Okay, Assalamu alaikum, Shabab. Welcome back. I hope you had an enjoyable long weekend. Enjoys the celebration. It was very nice around. Today, Shabab, we are going to talk about the last topic in chapter number 3. And we're not going to spend too much time on it. I'm just going to explain it. It's very straightforward. Simple equation, you apply it, and then you get the answer. But this topic is very important for our industry, just like the pressure vessel, because press and shrink fits is a very common joining method for machinery. So let me, start by some motivation over here. يا شباب انتوا تدروا بانه turbines for example are one of the most important machines around. We use them to fly, and we use them to generate electricity for most part, at least in the kingdom. So they are very, very, very important. Now, in principle, you understand, all of you, that turbines operate by one simple concept. You blow air, and then the turbine has a shaft with something like a fan, you want to say, blades, we call them. And then those blades, when they get hit by superheated air under high pressure, they rotate. That's it. And when they rotate the shaft. Then that mechanical rotation is converted into electricity by motor. Now, if you wonder how much are the stresses generated on those, we're talking about a tremendous amount of energy in terms of torque, pressure, and so on. So if you think about a simple shaft like this, and then on top there is this blade, and the superheated air or flow come and hit them. Of course, there is a casing over here, and then this shaft end up being rotating. The idea is this: it might be, and which is true, it's not a might, it's a true, that how there is no better way to clamp this on the shaft, okay, other than a press and shrink fit. There are many reasons why. First of all, the amount of torque is so huge. And if you think about nailing this by bolts, you put bolts over here, they may get sheared off so easily. Not only this, if you put hundreds of bolts, as much as you can, within that diameter, okay, you will generate a lot of stress concentration. And funny is that this stress concentration is going to be mostly around the surface, because this is where the bolts are. They are around the surface. And by doing so, you're actually killing your machine, because in the location where you have most of the stresses, you're actually generating holes and threads. And so it's a very inconvenient way. Now, shaft for turbines can cost you from several $100,000 to millions of dollars. That's only the shaft. If you talk about the blades, this part of the turbine is so big, is like a ring, and inside it there are little tiny blades. Each one of them, I heard from the industry, might cost minimum of $10,000. That's the minimum. Okay, there are of course turbines which have 7 stages. You can walk on them. You can walk inside the turbine. تتوقعون يا شباب if you go to Graya plant or other which generate energy that empower maybe the eastern region and even part of Riyadh, or let's say the eastern region. It's a lot. And they don't have thousands of turbines. They have, you know, a couple, like 8, 7, I think, or 10, but they are humongous. So how do we clamp this together? If this blade is not attached to the shaft very well, it's not going to rotate the shaft. So one of the best clean ways is to do it through shrink fit. That's it. How? Well, if you go to the machine shop for Aramco, which is just our neighbor, you might get an opportunity one day to visit them. What they do, when they dismantle a turbine, and I'm not talking about a very huge one, I am talking about one with a shaft of like several meters, you know, like 2-3 meters long, and there is like 10 or 8 stages. So what they do, they clamp and hang the shaft by a crane, with the shaft having those blades, which are the stages like this. They put some wood underneath, and then they bring a torch. تعرفون التورch يا شباب is a flame, and they start flaming the blades. The blades are not thick like the shaft, and they have a big surface area. So they start flaming them around and around. Their temperature increases, and then the clearances here open up, and then the blade will fall down. It's not going to get damaged. If it falls down in wood, it's nothing. They take the blade, then they torch the second one, it falls down, and then the third one, and then the fifth one, and so on and so on. Then they go and fix those blades or impellers. Sometimes they have different names. So those impellers, they get them fixed, they get the shaft fixed, and then what do? They heat them again with the proper tools. They start sliding them inside the shaft and then leaving them until they cool down. When they cool down, what will happen, ya shabab? They will shrink. And when they shrink, they will push on the shaft, and that's how the clamping happens. Very simple. Very simple. And no holes, nothing. The only thing that you need to worry about is when you slide down that's why shaft, as we are going to explain in chapter number 7, they have steps like this. Why? One of the reasons why we have a step is that when you slide an impeller, you push it. I mean, it is elevated. It's at elevated temperature. Maybe the temperature of the impeller is like 400 degrees or something. And the technician will wear special gloves, and they will push it with their hand or with tools. But how do they know if it is actually sitting in the right place? Through the step. They push the impeller until it hit the step, and it cannot go further, and then they leave it. Few minutes, it cool down, and then it will jam. Okay, it will clamp on. Now, how did this happen? Very simple. Very simple. A little mismatch. How? If you think about it, what are we going to discuss now is like the opposite. What do we have? We have an outer radius or an outer ring, and we want to squeeze an inside ring or pipe through it. Now, what happened is that if you look at delta over there, I know this may not be very clear, but basically the red part is here. That's the projection. The black part is here. So how do you fit them? Well, إما إنك تبرد هذا أو إنك ترفع درجة حرارة هذا. So this one, the temperature, you need to raise it up, or this one, the temperature, you need to lower it down. Now, it turns out that dealing with heat is easier than dealing with cold, because heat is very simple. You bring a cylinder of a gas and air, you mix them, and you can heat things. When you finish, you close the torch. No residual, no corrosion, nothing. If you use, for example, cold ice or something, even if it is a dry ice, it will end up being melted and you will have liquids around and so on, not clean. So what we used to do, we use heat. And when we use heat, this one is gonna get a little bit bigger. So that part is gone now. Okay. And now what we can do, we can slide the black one here. Now, once this one cools down, there is going to be a bush in here, right? The red one is trying to clamp, so it will push in this direction, okay? While the black one, انت قاعد تضغط عليه، فايش يسوي هو؟ Is trying to stretch. So one of them is trying to stretch, the other one is trying to clamp. In the end of the day, you created a clamping force. That's it. Now, you may wonder, is it enough? Yeah, if you do the math right, you will generate a huge clamping force there. No need for bolts, nothing. So what happened is this. I want you to focus on the mechanics of the problem. So what are we going to do? Assuming that all deformations are elastic. Now, if you look carefully over here, this radius, which is for the outer, ya shabab, this one, we call it R0. And the radius from the center to the common circumference, where they are gonna match, which is from here to there, we will call it capital R. And then the radius for the inner part is going to be called what? Ri. So what happened over here is this. We have the big ring, if you think about it. It has an R0 and capital R. And we have the small ring, which has Ri and capital R. That's it. That's what we have. Now, what is the stress that's going to be generated? Is the tangential stress, okay? So the stresses resulting from this pressure are found as follows. The tangential stress at the transition radius, the tangential stress is going to occur over here, right at the interface, where they are going to meet, both of them. So if you look at the tangential stress, we are saying here the tangential stress on the inner part. Why? لأنه this is the inner part and this one is the outer part. They are going to meet in this green region, but the stresses are related to the material which is being pushed. So هنا يا شباب, for the inner part, what do we have? We have sigma t for the inner part. The location is where? Is at R equals to capital R. R is any radius, but we want to find the stresses generated at the interface, okay? So at location R equals to capital R, we will have negative P, a pressure, so there will be a pressure applied, and then we have a geometrical quantity which is only function of what? يا شباب inner part, the inner part, which I'm gonna draw again, this is the inner part. Let's for the sake of assumption over here, or no, you know, I want to stick with the example. I don't want to confuse you. The inner part has Ri and R0. So this one is only related to the geometry, only R capital and Ri. And then we have the pressure. Now what happened to the outer part? The outer part, ya shabab, has an inside radius, which is, let me draw it better. Just be patient with me. So we have R capital and R O. So again, what do we have? We have a geometrical part where it is function only of the radii, and then the pressure. لاحظوا يا شباب اللي فوق حيكون under tension, اللي في الأسفل حيكون under compression. Okay, so this is the tangential stress for the outer part, not the inner part, at the same location. So the same location, one of them will be under tension, the other one will be under compression. Okay, now what do we want to know also? So this is the amount of stresses. طبعا يا شباب لو تجيك مسألة تجي تقول طيب أنا إذا طلعت التangential stress وش أسوي بعدين? What should I do? Well, you use this stress to analyze your material. فمثلا, for example, if the inner part and the outer part are made from, let's say, steel, you want to know this stress which is generated, is it going to be the failure stress? يعني ما ينفع أنت you generate stresses which are too much. It might cause cracking, it might cause yielding, and so on. So you want to know the stress. طبعا إلى الآن يا شباب إحنا whenever we teach you is how to calculate stresses. How to calculate stresses always. In the next chapter, which we are going to start today, we will teach you what does those stress, what do those stress means, because until now we're not talking about material property, we're not talking about material behavior. كل اللي نبقى نسوي ان احنا نعرف stresses. زي لما يا شباب في الديناميك كنتوا you solve a problem and you find velocities, you find acceleration. What does that mean? Huh? In the end of the day, if a body is moving with a certain velocity or moving with a certain acceleration, what does that mean? Well, our purpose is to find these relations, forces, stresses, accelerations, and then put them in a body. The body has a capacity. It cannot accelerate more than this. It cannot sustain a load more than that or stress more than that. So that's the whole purpose. Now, what is important is this. How do you know how much is this little delta? This little delta, since it is a value measured along the radius, we will call it the radial interference. Okay? The radial interference is how much is this little extra or little less we can have. Maybe, ya shabab, you will have the delta big enough such that when you heat the part, it will expand and then it will not expand anymore unless you melt it. So delta is too much. And maybe delta is so small where whenever you heat it with like 100 degrees only, just a little bit, the inner part will slide in, but you will not get very significant clamping force. So the delta, ya shabab, if you look at it here, is brought up for you in terms of both the outer diameter, the outer radius, or I mean the outer material and the inner material. We have E outer and EI. Those are the modulus of elasticity and for both materials. And then we have R0 and capital R, and we have Ri and capital R. No big deal. Here we have the pressure, which is going to be generated at the press or at the shrink fit. And also we have the Poisson's ratio. Let me take off the what did I do? Let me take off the circle from here. The negative sign has nothing to do with the Poisson's ratio itself. The Poisson's ratio in U out and in UI is the Poisson's ratio. If you remember from CE203, the Poisson's ratio for steel, for example, is commonly known as 0.3, while it is 0.33 for aluminums and 0.35 for magnesium and so on. So those are the elastic property of the material. And then we have a geometrical part. Now you may ask, how do we use this equation? Well, if you think about it, for most part, okay, we would like to maybe use a trial and error. Maybe, I'm not saying that this is how are you going to use it. But for most part, what do? We say that delta is equal to P, and then we put R over O0, the big parenthesis, and then R over AI, and then the big parenthesis. And then what happened is this. We want usually to know the pressure. So what can you do? If you solve for pressure, okay, the equation will be like this. It will be, which is equal to delta divided by all of this in here. Now, so the radii will be the same. تستغرب تقول طيب الانترفيرنس صغير. أقول لك yeah, it's not, you can put R capital, R0 and Ri. You can adjust them based on the interference. Okay, it's like, for example, if you have Ri, you can add to it the interference if you want, which is 0.00 something. But what is important here is this. While you are playing with the interference, you would know the amount of pressure that will be generated. And by knowing the pressure which is generated, you will know if this is good enough or not for you, if you want to design a shrink fit. Now, that previous equation can be simplified if we have E0 equals to EI and nu 0 equals to nu I. What does that mean? It means that the inner and the outer are made from the same material. In that case, I don't need to put EI or E out. I can just put it E, and I don't need to have in nu, but nu actually will cancel out, and you will end up with a relation of a pressure equals to the modulus of elasticity for both, materials. Delta is the interference, and then R is the radius of the interference, and then we have the outer radius and the inner radius, the rest of the relation. Okay, so I am not going to solve this problem. I'm just gonna explain it to you quickly over here. So this equation, ya shabab, is telling you that there are two cylinders of different materials and dimension. Different materials, not the same material, are joined by shrink fit. The elastic constants for the materials as well as the dimensions are. So we have the inner radius with di and do equals to 0 and 1.002. The material is steel. The outer cylinder with a di capital and do capital, which is 1 and 2. Okay, these are, if I'm not wrong, I think I need to fix the writing for this. These are in inches. And what do we know? We want to identify the interference, the radial interference, and we want to know the pressure at the interface, at the interface. Now, what you should do go to the back of the yes.
لا بس كان يقطع عندي.
شباب or maybe you Faris has a problem in the internet.
لا
قطع كذا ثانية بس.
كله دكتور الصوت قطع.
Okay. Is it good now?
Yes,
yes, it's good.
Okay. So what I was saying is that for this problem, we have been given the dimensions as diameters, not radii. So you need to be very careful. This is steel, this is cast iron, and no interference was given to us. We were given a dimension though, with a little bit of extra. 0.002 is actually the interference. So let me quickly highlight this. The solution is already on the slide. I uploaded the slide with the solution, so you will see it there. But just to walk you through the problem together, if you go to the back of the book and search for the Poisson's ratio for the steel, you will find it to be 0.292, which is nearly 0.3. And if you go and find the Poisson's ratio for the outer one, which is cast iron, you will find it to be 0.211. Okay? The modulus of elasticity for steel in BSI is 30 multiplied by 10 to the power 6 BSI. Okay? The modulus of elasticity for cast iron in BSI is 14.5 multiplied by 10 to the power 6 BSI. Okay? Now, the radial interference, ya shabab, is between the outer diameter of the inner circle and the inner diameter of the outer circle. So what happened is this. It is actually delta is equal to 1/2 multiplied by 1.002 minus 0.001. Basically, radial interference, ya shabab, is 0.002. But because it was given as a diameter, the interference is actually half of that. Do you understand it? Okay. Now, the inner radius Ri, now لاحظوا يا شباب, is equal to 0. The capital R is 0.5. And the big, the R0 is equals to 1. How? Let me show you. هذا يا شباب, the inner diameter is solid. It is solid. ما في RI. RI is 0. We only have R, which is capital, and now R is equal to how much? How much do I say R is equal to? Is 0.5. 0.5 is 1 divided by 2. لاحظوا يا أخوان, ال 0.002, I don't need to include it. Okay? R is the radius without the interference. Okay? The radius at the interference. Now, for the other one, what do we have? We have R capital and R0. Now, for R capital, we have it the same, which is 0.5. And for R0, it is 2 divided by 2, which is 1. That's why we have it as 1 over here. خلاص خلصنا. الآن, all what you need to do is to go and find the pressure. The pressure, يا شباب, is, if you remember, we can use this equation. This one. If you now remember, we have E0, we have EI, we have Poisson's ratio for both, we have capital R, we have RI is 0, so we don't need it. That's going to make it easier on us. We have R, we have R0, so and we have delta, which is 0.001. So the only unknown is the pressure. So if you solve this problem, you will find the pressure as 13,064 psi. Then what you need to do is to find the tangential. Yes, يا أحمد.
دكتور ال 0.001 هنا كيف جبت من فين جبتها هذه؟
هذه
اللي هو 1. ايوه هذه تمام.
No. That's I'm sorry يا شباب. Thank you يا أحمد. This is 1. Sorry. أنا كتبت What did I do again? This is 1. Thank you يا أحمد. This one is 1.00. The result is 0.001. Okay, which is the delta. Okay. So the next part is to find sigma tangential for the outer and sigma tangential for the inner. Okay, you will find that the outer one will have a tangential stress of 21,770 psi, and the outer one and the inner one will have minus 13,064 psi. One of them is negative, means is under compression. The other one is under tension. Okay, and the values are different. Why? Because of these equation. Look at this. This equation is different than this. It has Ri and R. This one has R0 and R. So different values will make you different stresses. Any question, ya shabab? Okay. Now, what are we going to do? We are going to move to chapter number 5. طبعا لا تستغربون لو مثلا سألتوا طالب أخذ الكورس من قبل يقول لكم إنه إحنا أخذنا chapter 4 after chapter number 3. It is debatable. يعني it's the same. We think it is more logical to go to chapter 5 and then return to chapter 4, as this is the recommendation by the coordinator, and we are going to follow it up, okay? Just to make sure that we are all aligned with all sections. So now we are going to talk about chapter number 5, but before we do that, let me take this moment and get rid of the attendance. Can you please switch on your webcams, ya shabab? While I am preparing this and you are getting ready, you probably know that I made the submission link for the homework. You can do it there. I would like to ask you to follow the instruction I gave you before, either to use your scanner, a legit scanner, or you use the app that I showed you earlier. What else is this? Yes?
Victor, can you postpone the deadline for the quiz for today, just for إلى الساعة 12 الليل أقصد.
Somebody asked me about this. Inshallah, I will let you know too soon. Okay, I will talk to the coordinator, and once I confirm it, I will post it. Okay.
Okay, thank you.
Okay, thank you.
Also, we are gonna have the quiz on Thursday, ya shabab, not Tuesday. The material is until more circle, didn't change. We will have the same arrangement, ya shabab, for the quiz, similar to the arrangement for quiz number 1. يعني الأسئلة راح تختلف. عشان كذا يا أخوان, what I want you to do is to make sure that your connection is stable and you don't get disconnected, because when you log out from the quiz and you come back to it again, you will get a different question each time. And I know this is confusing for me while I'm grading, and it's confusing for you. I had students with appearing in different questions, which was very confusing. Anyway, let's get rid of that in this. Faisal?
Yes.
Where are you, Faisal? Faisal, حياك الله. You, Yusuf?
موجود دكتور.
Okay, Hamad.
Yes, doctor.
Hamad, I'm trying. Yeah, Hamad, I see you. Ali القحطاني.
Yes, doctor.
Yusuf, Yusuf.
Yes, doctor.
Majid, can see you.
Yes, I'm here.
Ali. حسين.
Yes, doctor.
العلي. Okay. محمد.
موجود.
Okay. حسن.
Yes.
عايش.
موجود.
مبارك. مبارك, where are you? Hello? Did I get disconnected?
No, I can hear you.
Where are you? Mubarak, are you here?
لا نسمعك يا دكتور.
Okay. Mubarak, I'm signing you absent if you are not calling me back. Okay. Ahmed?
Yes, sir.
Okay. الحجي?
الحاجي دكتور.
الحاجي, where are you? Okay, here. معجب?
Yes, doctor here.
سلطان?
موجود يا
حربي؟
دكتور. موجود.
عبد الله؟ جاب.
Yes, موجود.
سلطان؟ موجود. سلطان, where are you?
المايك شغال؟
Yeah, I can see you. فارس?
Yes, موجود.
And عبد الرحمن?
Yes, doctor.
خالد العتيبي؟
Yes, doctor.
عبد الله العوفي؟
Yes, doctor.
فارس القحطاني؟ فارس؟ ثابت؟
Yes, doctor.
علي الرمضان؟
Yes, doctor.
هاشم؟
Yes.
سادة ماجد؟
Yes, doctor.
Majid, where are
Yes.
you? I'm trying to find you.
No.
Yes, doctor, I'm here.
Yeah, okay, I can see you now. Muhammad?
Yes, doctor, I'm here.
Ahmed Sultan?
Yes, doctor.
مشعل يامي؟ مشعل؟ وليد؟
Yes, doctor.
محمد؟
Yes, doctor.
ورشيد? Okay. Abdullah?
Yes, doctor.
And Ahmed?
موجود.
Okay, thank you يا شباب.
Doctor.
Yes.
Sorry, I missed.
And who are you?
I'm Faris. Faris القحطاني.
Where were you, Faris?
I was at bathroom. Excuse me.
Okay. All right. So what I was saying, yeah, Shabab, is that I'm gonna post the announcement for the quiz. We're gonna have it on Thursday. So.
دكتور ما تقدر تأجل الكويز مثلا.
كيف؟
ما يتأجل الكويز إلى يوم الأحد مثلا على 3.
This is gonna be too late for you, يا شباب. But I mean, we will, if we make it next Sunday, next Sunday we should have a quiz number 3. And even if we have based on the plan, it should be Sunday, 4th of October. But since we are going to have the quiz on Thursday, 1st of October, I will probably push quiz number 3 to the Thursday after. I hate to have 2 quizzes side by side. There is no way, ya shabab. Unfortunately, we got trapped. And if we keep postponing, we will not have the same number of quizzes as you want it. And ya shabab, as far as I know, you don't want to have the quizzes of hours. يعني في الليل, في العصر. And I have to do them in the class time. Otherwise, students will complain. Because it's true. I mean, if all of us make the quizzes on night, you will be working the whole day in the morning, afternoon. And at night, you will be working all night on quizzes. So unfortunately, there is no choice. Okay? I think until Thursday, ya shabab, if you use a micro-study plan, which is every day you study half an hour or 1 hour, believe me, it is going to happen easily. But if you think انه لا لازم خلاص الكويز يوم الخميس يعني معناها لازم اذاكر يوم الاربعاء, it might be too much. Okay. What would you want me to do? Do you want me to drop the number of quizzes and then we have 15% divided by 4 quizzes, for example? Everybody will be angry.
No, Doctor, no.
It has to happen. You need to work it out. حتى لو تذاكر ربع ساعة يوميا للكويز اليوم وبكرة واللي بعده. Try to learn. Okay. Today, I mean, within the remaining 9 minutes, we are going to introduce you to chapter number 5, which is failure resulting from static loading. Now, failure is very, very important because that's why we design things. I mean, we design them, احنا engineers, not to fail. If they fail, it's a problem. We don't design things because they look nice. We maybe hire another team to make them look nice so people will spend money on them, but they have to function properly in an engineering sense. Now, this is talking about failure resulting from a static load. Static loading يا شباب هو اللود اللي في الحقيقة ما يتغير بشكل سريع. ليه؟ لأنه على سبيل المثال the famous tension experiment is considered to be failure, is considered to characterize the material under static loading. However, if you look at the screen when you run the test, you will see that the load is increasing. It's not static. احنا ما جينا وحطينا 100 كيلو نيوتن وخلصنا. لا, it is 0, then 10, then 20, then 30, then... So, in proper terms, we call it quasi-static. معناها إنه هو زي الستاتيك لكنه مو في الحقيقة static. What does that mean? It means that it is not too fast to become impact. It is not too slow to become creep. That's what does it mean. الكريب يا شباب إنك أنت تيجي you put a load and then that load you leave it for a long time and then the load will break the material. There is another way, which is applying the load suddenly, very fast. That's impact. There is another way, which is applying the load in a cyclic fashion, which is chapter number 6. We're not going to talk about it today. Today, we're talking about static loading. Now, in reality, يا شباب, إذا تروح للسيارة مثال أو الطيارة أو القطار robot, anything. Actually, يا شباب, إحنا we don't design static structures. Mostly. Civil engineers, in some sense, does. Buildings are building. Although there are some loading, you know, temperature, people get in the building, there are earthquakes. So it's not isolated. But in general, we design machines that move. And when they move, the load changes as you move. And so why do we need to worry about static loading? Well, this is a necessary but not sufficient condition. That's the end of it. يعني ما ينفع يا شباب انك تسوي ماشين which operate for impact or cyclic loading without checking the static loading. Static loading is always necessary. You need to do it before you do the other work. Now, so if we talk about failure with respect to static loading, it makes a lot of sense to talk about static, it makes a lot of sense to talk about static strength. So that's what we are going to do. We're going to talk a little bit about static strength. This is supposed to be removed. We're not going to talk about it. Then we'll talk about failure theories. The failure theories are basically divided into ductile material and brittle materials. That's it. This is the summary. We'll talk about 3 theories for ductile materials, and then we will talk about 2 theories for brittle materials. A static load, ya shabab, is a stationary load or force or coupled, like a moment, okay? It is applied, and then if it is high enough, it can cause damage, just like a tensile fracture. And with respect to failure, it's very hard to define. ليه يا شباب؟ لأنه as we move on with the course, you will see that there are failures that doesn't necessarily mean إنه الآلة متكسرة أمامك. يعني أنت you go to the machine shop for your car and you change some parts. But if you look at them, they are not shattered into pieces. They have a little damage, but that little damage is considered to be failure. With respect to static loading, ya shabab, with respect to this course, we will mostly assume that failure is not this one, it is not this one. No. We will mostly assume that failure is actually this, or sometimes the ultimate. But for most part, we consider yielding as failure. You see that يا شباب؟ طبعا احنا كلنا نعرف as mechanical engineers that yielding is just 2% of the whole thing. There is a lot ahead of the material. But since this a lot is involving a plastic deformation, which is irreversible, يعني باختصار إذا إحنا حنجيب مثال مضحك شوية، أنت تروح تشتري مرسيدس بنص مليون، وبعد ما after you drive it in a long highway, it gets subjected to a lot of stresses and deformation. You park it, you sleep, you come back, oh, المرسيدس صار كوريلا. That's just like a joke. What happened to your Mercedes? It went under plastic deformation. This is not acceptable. So we design for most part under elastic deformation. That's at least the assumption, okay? Now, so what are we going to do? We need to classify materials based on their behavior. واحد من البيهيفير اللي تكلمنا عنه يا شباب هو موضوع ductility. If you remember, we said ductile material are sensitive to shear. A brittle material are sensitive to normal stress. So how do we know that? Well, in this book, we will treat brittle material as the material that has fracture strain which is less than 0.05. This is dimensionless, huh, ya shabab? It is not, which is 5. This is, how much, ya shabab, is this in terms of percentage?
5%.
5%. That's a 5% deformation. يعني إذا عندك material which rupture here وتحسب ال strain in the rupture, if it is less than 5%, then this is a brittle material. If it is higher than 5%, then this is a ductile material. That's number one. عندنا another class. What is it? إنه إحنا تعودنا إنه الماتيريال عندها tensile yield، صح ولا لا؟ sigma yield. Well, material also have compressive yield. So some materials have Yielding and tension, different than yielding and compression. So this is a new class of material we are going to talk about. If the material in hand has different compression and tension or compression, then the material will be treated differently. Same thing, some material have ultimate strength and tension, which we will call SUT, different than ultimate in compression. And if that's the case, then we will also treat this material differently. So it will be very clear. انت بتيجي وبتعرف تقول هل الماتيريال brittle ولا ductile? If it is ductile, هل ال yield stress is the same in tension or compression? Or it is different, and you will know which theory you should use. The theories طبعا يا شباب in last 30 seconds. Theory is actually very simple. الثيري هي عبارة عن معادلة. It's an equation which will tell you, give me the stresses. اعطيني stresses. Put them inside the equation. You will get a number. If this number is more than that, then it is safe. If it is less than this, it is not safe. The question هنا وين? What are the stresses? So you will need to use more circle, tension, bending, shear, all of what we did in chapter 3 to find the stresses and then plug them inside the equation. Understood, ya akhwan? Thank you so much. See you next class, inshallah.